Good evening, everyone. It's a sharp 6 p.m. We are starting. This is Hari on behalf of Springboard Technologies. It's the eighth webinar event for the Campus to Corporate VLS webinar series. And we have 12 different topics in all the aspects of VLS chip design. And there are 12 distinguished speakers from the various reputed companies. This is our team. This is Hari Seshadri. And we have Madhubala, part of the Springboard Technologies on the team. Hi, Madhu.
Hi, everyone.
And we have other partners, other organizing team members. They are not in this meeting from IEEE and Sevalaya. This webinar is coming to you in partnership with IEEE BLP and with Sevalaya NGO. All right, and I'll skip. So we want to thank all our donors and sponsors and partners. Get into goals professionally, led by Swaroop and Sri Venkateshwara College of Engineering. It's affiliated with Anna University in Chennai. And Airmeet Technologies, thanks for the wonderful platform provided by Airmeet. We have SEER Academy, one of our partners. And we have Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram. And we have Chennai Institute of Technology, one of the premier colleges in Chennai. And we have MentorCart, like mentorship platforms, one of our partners. We have Spica Works and Adapt Chips, one of the semiconductor companies, also partners for this particular webinar series. And we also want to thank all the volunteers who have been put tireless efforts to put on this event for the last couple of months. We want to thank all of them. And we will encourage all the people like attending the webinar to donate any amount voluntary to say Sevalaya, the NGO. The money, whatever you donate, goes towards the skill development for the rural youth. They are impacted by COVID, so they are training some vocational trainings. After a period of 4 months, they become employable in reputed companies like Tata's and those kind of companies. Right? There's a link you can go and donate, and just mention that the occasion message column. Just mention C2C VLSI. And then then you can email us in our emailing thing, so we can help you to get the receipts and everything. So I'm very happy to invite Mrs. Punita. This is Punita Pradeep. She's the founder and director of Ampisoft Technologies. They're very interesting model. So they have a unique product called eBox, which is being used by reputed corporates and also the academic institutes. It's basically learning is in a different way. It's a very automated mobility-based learning, and with gamified learning and all those things. It's pretty making the education and skill development very interesting, right? And they pretty much work on the software domain. And please visit the episode website for more details. And she has done her master's in Amrita Institute in Coimbatore, and her passion has been on the skill development and providing better education, how we can add a value to the student's life, right? So the Ampisoft Technology is there for last 11 years, and they're doing quite a good work. They are over 150 member team, and they're pretty much successful today, right? Welcome, Preeta.
Yeah, thank you, Hari.
So over to you.
Yeah, thanks, Hari, and thanks, Madhu, for inviting me for this session. It's a very interesting initiative, and today I'm glad to introduce the speaker of the day, Mr. Sudheer Reddy. He completed his MTech in microelectronics from IIT Kanpur, and later he has worked in different semiconductor industries, the leading ones like Intel, Qualcomm, ST Microelectronics, SmartPlay, and Cisco. And he has more than 2 decades of experience in semiconductor industry with expertise in ASIC and SOC physical design. And he has worked on many major designs targeted for various applications like networking, mobile, wireless, etc. And he has managed many teams. He has led many engineering teams for SOC design and implementation in various companies that has been a part of. And now in the year 2020, he has founded a company named SemiConnect Tech India Private Limited, where he aggregates a group of freelancers and he provides a platform for semiconductor experts to share the knowledge that they have derived from years of experience. We welcome you, Sudheer.
Thank you, Punita. Thank you so much.
Sudheer, you can share your presentation.
Sure, I'll start sharing. You need to enable me to share.
You have to just share, that's all. Able to share?
The share is not enabled.
There's the third button on the
yeah, but it's not enabled actually.
Did you stop sharing yours?
Yeah, I did. You're not seeing my screen, right?
I'm not seeing your screen.
Yeah, you can share.
You might just want to refresh once.
Should
It
I share?
usually works.
Yeah, I can share his PPT otherwise. Yeah, space. Let's see. Sorry for the delay, guys. Just a minute.
Okay, somehow I'm not able to share.
So let me go and share it, Sudheer, for you then, right? You just say, just guide me next
I
time.
think it's better I share it.
Yeah, I know.
I'm not sure why you're not able to share.
You're just able to share minutes before, right?
Yeah. The share is not enabled. It is grayed out.
So this I recommend we got started so we'll lose the time otherwise, right?
Okay, all right. We'll get started.
Yeah, just one second. I'll turn off my video and share. 1 second.
We're all still here, guys. We're just waiting for the presentation to be shared. Yes.
Okay, so yeah, without much further delay, let's get started. Objective of today's discussion is to talk about physical design, ASIC and SOC physical design. I'll start with the definition and what is the significance of physical design in overall chip design process, and then we talk about how the complexities in nanometer era. We call it nanometer era because the channel lengths today are in nanometers. And then we talk about hierarchical approach, which is helping solve the complexity that we have. And then I'll give you a physical design flow overview. And I'll try to explain that flow with an analogy so that people can understand better. First time who are listening to this physical design aspects, they may be able to correlate well with an analogy. And then at the end, I'll also touch upon industry expectations from fresh graduates for a physical design engineering question. So to define physical design, if you look at chip design process, somebody thinks about an idea or an application and they want to make a chip for it. So first thing that you would want to do is to find out what is the logic that you have to use for the defined functionality. So you do the logic design and then you have to manufacture silicon. So you have a logic design and you want to manufacture silicon. If you give logic design to a manufacturing foundry, they'll not be able to give you a silicon. So they need a geometrical information which they will be able to manufacture. So the process of transforming this logic design into a geometrical data is what we call it physical design. While you do that transformation, you also need to make sure you meet the functional, electrical, timing, physical, manufacturing, and reliability parameters. So in an essence, what we are saying is you have a logic defined in a code like a C-like code or Verilog HDL. It's an RTL code, and that get translated into a layout information, which foundries will be able to take and manufacture the silicon. In an essence, this is what we do in physical design. So physical design, we also have different names used in the industry. I just wanted to highlight those as well so that in case you hear these terms in the industry, you will know that this is what we are referring to. So people use it, call it as chip layout design, place and route, or auto place and route, chip implementation, ASIC SOC backend design, or RTL to GDS implementation. When you see any of these terms, all of them refer to physical design. Next. So I talked about different parameters that we have used in the definition, right? I want to explain each of those parameters so that you understand the significance of physical design. So we talked about functional parameters. What does that mean? So you have designed your chip to work for a different function. So you have set of inputs and you want to get the same outputs as a functionality of that chip. So once you have coded that RTL, physical design has to ensure the layout that you give to Foundry has the exact same functionality that you have intended to operate. So, and I'll give you a small nitty-gritty to explain the complexity as an example. For example, you are designing a shift encoder, and you have used 30-bit encoder to start with. And after some point of time, the designer may think, okay, 32-bit encoder is not sufficient. I want to expand it to 256-bit. So it's just a simple RTL change. You just remove 32 and put 256 in your RTL code. You are done. So functionality wise, it is defined. But is it so simple in physical design as well? No, it is not. So it can range from few thousand gates, can become millions of gates when you just change from 32 to 256. And on top of it, if you add timing, electrical parameters onto it, it becomes so complex and you may not be even able to implement this design with the code that we have. We may have to break it down. So that is the kind of complexity that we are talking about when we say we have to retain the functionality from a RTL code to the layout. And move on to the next parameter, electrical parameters. These are also very important. So when you define a functionality, you would have designed a particular functionality, but you won't know what are the operating voltages, what will be the power consumption. For example, if you are using the chip for a mobile application, you want to put this chip into a mobile phone versus you want to put it in a PC versus if you want to put it in a networking router in a data center. All these applications require different electrical um, parameters, and electrical design has to be different for these different applications. So physical design has to ensure all the electrical parameters required for chip operation are intact in terms of, okay, for example, I am supplying a voltage and there can be a voltage fluctuations from the voltage regulator. And we'll have to ensure in physical design that these voltage fluctuations are indeed taken care. When the silicon comes, it should be able to sustain the fluctuations and still operate and give you the respective functionality without fail. So that's in an essence is the complexity that we are talking about. I'm just talking about one complexity. There are several such electrical parameters that has to be kept intact for the chip to operate properly in silicon. The next is timing. So again, like I talked about, one chip can operate at a slower speed, faster speeds at different megahertz to gigahertz range, and the timing parameters have to be met in physical design for it to work at that operating frequencies. For example, you are designing a processor to work at 1 gigahertz or up to 1.5 gigahertz. You need to ensure that the logic functionality is one part of it, and it has to complete that functionality in a specified time that you have. Within that time frame, you have to get the outputs. That is what the timing parameters will ensure in physical design. There are several levels of complexity on how you meet your frequencies, and it's just not only the frequency or the speed of operation. Sometimes certain functionalities will not even work if they don't operate at certain frequencies. For example, if you're processing a audio signal, let's take an example of a mobile phone, right? You're talking and then the chip in the mobile phone has to process your speech data, and it has to real time send it across to a network, and then at the receiving end as well, you need to be able to receive that speech signal and process it and send it to the speaker so that the other person can hear. All of this has to happen real time. So there are time-bound protocols which are defined for all this to happen. And if those timing is not met, then your speech signals that you are transmitting will not be seamless. You will have breaks. So the functionality that you have defined will not.
Hari, I think we lost Sudheer.
Yeah, I think so. Lost connection. Yeah. You guys, please hold on. Yeah. Some network issues maybe. We're just telling about the timing problem. I think we have a real timing problem here.
Right. So I guess while we wait for Sudheer, we'll probably take a quick yes/no poll. We haven't used that in a while. So here's a question to all the attendees. Are you finding these webinars useful?
You're creating a poll, Madhu?
Yes. All right. Is Sudheer back?
Yeah. Sudhir, can you hear us? No, again we lost him. Who's coming again? Sudhir?
You guys hear me now?
Yeah, I can hear you. Yeah.
Okay. Timing parameters. I think we lost.
You can go to next slide.
You can go to the next slide. Physical parameters is physical design has to again different types of applications as well as the package, the aspect ratio rates. For example, if it is, it's operating some consumer operating conditions and into define ratio type of for a be taken into consideration. One. So this is very important. Use meter like in 2001 time frame we were 7 nanometer and 5 nanometer. If you look at the number of design rules that we have for all these technologies, maybe in 180 nanometer we had like 700, 800 rules, whereas in 7 nanometer we will have close to 15,000 rules, and maybe in 5 nanometer we have close to 20,000 rules. So that is the complexity of design rules that we have in today's technologies, and all those design rule parameters have to be met when we are doing physical design, so that when silicon is manufactured, it is intact and there are no faults, and we get proper silicon that works. So that is also ensured when we do physical design. We need to ensure manufacturability and all the manufacturing parameters are met. And last one, reliability. Again, the chip will be operating at different environmental conditions, voltage, temperatures, and so on. So when you put this chip in different operating environments, we still have to ensure it will work as we intended it to work. As
Yeah, Sudhir? We lost him again. Yeah. Okay, sorry about it. I think we have some network issues.
We have questions.
Should we take those questions? What I can answer? Should I answer them instead of timing?
Yeah, Hari, you want to take a go with it?
Yeah, processor works at 1 megahertz says the input to output delay max available. No, the answer to Sri Senthil's question on the processor works at 1 megahertz say, does it mean that input output delay, the max available in is 1 microsecond? Is that correct? No, that's not correct. When he says 1 megahertz, that particular clock period is whatever 1 microsecond. That's the time between the logic it can operate between one flip flop to the next flip flop. Right? It's not input to output of the chip. It's between the one flip flop to next flip flop. In the same flip flop, the clock to Q delay of the flip flop to the setup time of the next flip flop, the common amount of logic it can take is constrained by the correct clock period. How to go in physical design? Which subjects to focus? Yeah, you should know your CMOS fundamentals very well. And physical design is not taught in the colleges. So you will have to take a specialized training, right? So while you are in college or go to finishing school and take, or if your college has the tools like Cadence, mental graphics or synopsis tools, you could they might be teaching you. Mostly in masters or if you're in reputed colleges, they have the tool sets. Yeah, but unless you go through the training and you have to do not just training, but you have to work hands-on. You have to do certain projects, then we get the skills. Why is GDS format still used? Why not YSS? Yeah, I don't know what is YSS format. Madhu, do you know?
No, Hari.
Okay, let's wait for Sudheer to come. Yeah, there's a question on machine learning. Let me see if we can answer that. Yeah, machine learning is growing in the field of VLSI. What are the skills expected from fresher in order to get roles to work in machine learning? Wow. Okay, so machine learning, you should have a subject called machine learning. You should study that or look for what is machine learning. Machine learning is basically heuristics based, right? You have to get the data, analyze and take decisions, basically, right? So you have to analyze data analytics and machine learning. You take some courses. You look at some of the popular websites, Khan Academy. Look at the YouTube. There's a lot of courses must be there. A lot of organizations. So just drop an email to us. We'll help you if you want. There are standard courses available. You have to go through and you have to take them. Yeah, so GDS2 is a standard format everyone uses in the industry. I'm not sure the old or new, whatever. We have not heard about YSS, but that's how the standard format entire industry uses throughout the world is a GDS2 format, right? So any other questions? Hey, Sudheer.
Hi, Harry. I'm not sure I'm getting logged out.
Yeah, so is there a problem with your network?
No, I have a fair connection. There's no issue with the network, and I'm also checking the speeds. It's pretty good.
Okay. So we are just taking all the questions in your absence. Just to continue that, there was a question about what is YSS and GDS2. What is the difference?
Okay, sure. So ASIC and GDS2 are pretty much similar geometric information. GDS2 is a older format. OSIS is recent format that we are using probably since 2010-12 onwards. It can compress more data and it's highly compressed compared to GDS2. So OS is the latest format.
You can continue. You're talking about reliability, right?
All right. Sorry. Yeah. So again, chip has to ensure the reliability parameters are all met. So we can move on to the next slide, Hari. Okay. So with this, I wanted to give you a glimpse of what are the complexities that we are seeing in nanometer era. If you look at the size of transistor in 70s, it was anywhere between 10 to 100 micron. This is the transistor channel length. And if you look at size of transistors in 2020, it's 5 to 7 nanometer. That is the technology that we are working on now. So just to for you guys to appreciate what is 5 nanometer or 7 nanometer means, if you look at human hair, it's about 100 micron thickness. If you split a human hair vertically by 100 times, that gives you a 1 micron, which is equivalent of 1000 nanometers. And you split it vertically by another 100 times, then you get 10 nanometers. So if you really talk about a 5 nanometer transistor, that you are talking about 1/20th fraction of a human hair width. So that is the kind of technology that we are working on. So now you can understand the complexity of designs that we'll be doing. And I also want to give a glimpse of design sizes that we are talking about. If you look at Intel i7 processor, we have close to 3 billion transistors in that processor. And in a Snapdragon 865 SoC, we have close to 8.5 billions of transistors. So we are packing all this many number of transistors in a small chip of probably 150 square millimeters. So I also gave a comparison of how this technology is progressing over a period of time. If you compare a 8086 processor that you may have heard about or read about in your colleges versus latest Core i7 Intel Core i7 processor, which is released in 2017. If you compare the frequencies, transistors, so frequencies were in few megahertz versus the gigahertz frequencies that we have now. So it's almost 1000x. And transistors are like 29,000 versus 3 billion. So it's almost close to 100 million times, a million times more. And die sizes have not increased because you still want to keep the chip size small. So physical die sizes have not increased. It's maybe just 5 times, but the number of transistors have tremendously increased. So minimum feature size was close to 3.2 micron, and now it is in the 8 nanometer, which is almost again close to 1000x or maybe 500x. So similarly, memories that is supported within the processor was in megabytes, and now we are talking about few gigabytes. So this is the kind of complexity that we are talking about in a nanometer era. So when you have such a complexity, I wanted to see, is there any other similar complexity that we have in a real world? I was talking to my son and I asked him, have you heard about anything around 8.5 billion? He said, yeah, maybe number of stars in the sky. So maybe that's into trillions, maybe that's even bigger number. Any other number? Then I thought about the population that we have on the earth. Hari, if you go next. So if you look at our world population over a few years now, in 1800s we have close to a billion population. In 1900s we have close to 1.6 billion, 1900 year, and in year 2020 we have close to 8 billions. This is a similar complexity that we are talking about, the number of transistors in the chip versus the population in the world. So I wanted to derive a similarity between the world population and number of transistors on a chip to see how we are trying to solve the problem in physical design to accommodate so many chips on a chip, so many transistors on a chip. So let's go to the next page. So one of the key important aspect in physical design is designing hierarchically. So let's compare how the world population and transistors go. Let's say at level 1 we have transistors and number of people. Level 2, where you have logic gates, which consists of multiple transistors, and I can compare that with an apartment or a house. If you go to the next level, we have logic clusters or regions or modules or partitions. These are the terminology that we use for different hierarchies in a design. I just wanted you guys to get familiar. If you translate them to equivalent things in the world population side, You can probably equate logic clusters to streets, modules to localities, and then partitions to towns and cities. And you go to a next level of hierarchy, you have partitions or super blocks, and on the other side you can correlate that to the states that we have. And then if you go to the next level of hierarchy, it's like subchips or subsystems, which you can probably correlate to the countries and continents that we have. And then next level of hierarchy, if you look at it, that gives you the full chip or SOC, which equates to the world that we have. So if you look at the world population, how it is organized into different hierarchies, similar way we can organize our transistors into different hierarchies on a chip. So I just want to give you a glimpse of how they look in a layout or how they look on a chip. If you look at the rightmost thing, you have a circle, that's where the transistor is, and then that is embedded in a gate. And that gate, multiple gates placed in a logic cluster is where you have a logic cluster. And then several such logic clusters will form a module, and several modules will form a block or a partition. And then several such blocks and partitions will form a subchip or a super partition. We call it as a subsystem. And then those several subsystems will form a SOC. So that is how we are segregating a bigger picture into a smaller portions, smaller chunks, and it's basically divide and then conquer. And then we make the problem smaller and then try to solve the problem at a localized level. So the hierarchical approach is the key ingredient for us to solve such a complex design problems that we have in physical design. So at this point, I want to give you an overview of the overall physical design flow. So if you look at it, the first step that we start a physical design process is with the synthesis. So I have explanation for each of these blocks, but I'll just give you an overview. We start with the synthesis, then we do floor plan, partitioning, and power plan. Then we do placement, then we do clock tree synthesis, routing, and sign-off checks. Sign-off checks is where we make sure all the parameters that we discussed in the definition of physical design, all those parameters are checked. And I'm showing this the circular symbols just to tell you that this is an iterative process. This is not like one time you do everything. So you do, for example, you do floor planning, placement, clock tree synthesis, but then you may not meet your, after synthesis you have not met your timing or power parameters, for example, then which you may have to go back and redo the floor plan. So that's why all the steps are iterative, in the sense we may go back and then redo again and then come back until we get the desired results. So the entire flow is an iterative process, but eventually we have to go through this flow of steps like floor plan, placement, clock tree synthesis, routing, and sign off to get to the sign off stage where we eventually meet all the physical design parameters. I have shown power and timing as a sidebars. These two are the key important aspects that we keep optimizing at each stage of the design. Okay, if we go to the next one. So what is synthesis? Synthesis is a process in which we take the RTL code and convert into a logic equivalent gate level netlist. We call it a gate level netlist, which is basically a set of gates connected, logic gates connected to derive the functionality. So if you have learned about any Boolean expression that can be implemented in logic gates, probably would have learned in your digital design. Similarly, any large complex functionality that is coded in RTL can be synthesized into gate level netlist. So synthesis is the process which does this. When you do synthesis, you need to make sure it's intact. And then if you have some low power design intent, that is also translated into gate level netlist. And after you have synthesized RTLs into a gate level netlist, the timing and power goals are met after synthesis. And then you also do physical synthesis. Nowadays, this is the complexity of physical design has become so much. At synthesis stage itself, you give a floor plan information to make sure you get a physical synthesis, so that you can finally able to achieve all the parameters that we have defined for physical design. So physical synthesis is an optional step, but predominantly more and more in latest technology nodes, we are using physical synthesis to get better synthesis results. So once you have a gate level netlist, the next step is to do floor planning and partitioning and power planning. So you first have to look at the size of the number. Let's say you have RTL code you have synthesized for the first time. You look at it. Let's say you have ended up with a million transistors, million gates. So based on that, you define the size and shape of the floor plan, and then you start floor planning a design. So where all the larger components like PLLs, memories, analog mixed signal, macros, all of these are placed in a floor plan, and your power elements, IOs, all this has to be put in a way that I'll explain you with an analogy so that you will get a better picture of how do we do floor planning. And then you also partition the design. Let's say your design is too big, then you break it into partitions. It can be subsystems, and the levels of hierarchy decided by the complexity of your chip. I have seen chips ranging from 4 levels of physical hierarchy to up to 7 levels of physical hierarchy. It depends on the size of the design that we have. And then you also do special routes and clock meshes during the floor plan stage. The next step is placement. So once you have defined your size, shapes, and regions and partitions, everything, then you start placing your logic gates. So mostly the placement is done automated with the EDA tools. So you place all the standard cell gates using automatic placement. And the key parameters that we have to look after placement is the timing, power, and congestion goals are met, so that you can proceed to the next stage. So congestion in the sense, you should be able to route all the connections with the given placement. That's what a congestion metric gives you. So you want to make sure you are able to route your design with the given placement. So that once you have done placement, you would have placed all your clock components. When I say clock elements, all the sequential elements in a design. So mostly we are working on synchronous designs. So you will have flip-flops and you have memories. All this work on a clock. Whenever the clock reaches these components, they store the logic. So in a sequential design, clock is very important. So that's where the clock tree synthesis comes into picture. So you have one clock input, or maybe a few clocks that are coming out of PLLs, which we will use for supplying it to all the sequential components in the design. And that's what is ensured in a clock tree synthesis. So the clock trees we call it tree because you just cannot route one signal into, let's say you have 100 million flip-flops in a design. So you cannot have one route going and feeding into 100 millions. It has to be properly buffered with multiple stage of buffering. And that is called a buffer tree. So that's why you call it as clock tree rather than just a clock. We ensure that timing and power goals are met after clock tree synthesis. The next step is routing. So once you have done your clock tree synthesis, you go for signal routing. So rest of all the signals are connected during the routing stage on different metal layers. So post route optimization is done to again check your timing and power parameters. All other manufacturing DRC parameters are all met. So that will ensure we have properly routed the design. Hi, Hari.
Hari, we're not able to see
Yeah,
the
I'm seeing
screen.
something happened. Yeah, just checking again. I know it broke automatically.
Okay, so now I'm able to say again. So moving on to the next step, once we have a routed design, we do all the sign objects. You remember we talked about different physical design parameters, functional, electrical, timing, physical, manufacturing, and reliability parameters. So how we check them is once you have complete routing is done, then you check for all these parameters. So we do what is called static timing analysis. That is to check all the timing and performance parameters of design. We do physical verification. This is to check whether all the physical and manufacturing parameters of the design are all intact. We do power and IR drop analysis. This is to ensure all electrical parameters are met in the design. And we do formal verification. This is to ensure all the functional parameters are met in the design. And we do reliability verification just to ensure all the reliability parameters are met. So when you have met all the parameters and you have completely laid out the design, that's when it is ready to, that geometric database, whether it is GDS or OSS, is ready to be handed over to Foundry. And we normally call this process as tape out. So you would hear this term tape out multiple places when you talk about physical design. So basically tape out means you are handing over a geometric information to Foundry to manufacture a chip. So that's overall physical design flow. Now, given that you have a chip like this, I want to use an analogy on how it is similar to city planning. So, for example, you have an SOC and you have a city. I wanted to take a planned city. Thought I'll take ancient example. I've taken a Mohenjo-daro city plan. So, if you look at how we go about partitioning a city, go next, Hari. So, if you look at city planning, right, you have a government buildings, you have administration, you have logistics, residential, commercial, entertainment, academics, the airports, railways, and corporate buildings or industrial buildings. All this you plan it in a way that everything gives you a better access and better approaches, right? For example, government buildings have to be closer to the administrative buildings or corporates or the airports and railways so that you have the connectivity. Residential buildings have to be closer to the commercial and entertainment and academia. Academia should be closer to the entertainment and commercial and administration. So you come up with a basic how do you partition a city. So similarly, if you come to a SOC, go to next one, Hari. Yeah. So if you look at an SOC, right? I've taken an example of a mobile SOC, which is used for a smartphone, right? You have multiple GPUs, CPUs, and AI processors. If you look at latest mobile chips, AI processor is becoming bigger and bigger. You have display processors, you have multimedia audio video processors, you have modem, which is the key 2G, 3G, 4G, 5G functionality, and you have data processing engines, PLLs, which are the basic analog mixed signal components. But you have all of this, you again have to come up with similar floor plan that you look at in a city plan. You have to come up with where you place your GPUs, where you place your CPUs in such a way that the connectivity and ease of access across all these functional blocks is easy. That's where the floor planning comes into picture. It's more of an art of how well you can plan your city as well as SOC, right? It comes with a lot of experience, and you'll get to know how you go about partitioning and floor planning your chip. So I thought I'll give you an analogy so that you understand what we do in SOC floor planning and partitioning. If you go to the next step, so once you have a city, you have identified where all the regions where things have to come. What is the next thing that you have to plan? You go next, Hari. So next thing that you will have to plan is how your water supply and drainage systems are built. So if you look at a city, you properly put all the channels for water supplies and drainages, so that you have, once you have built all the rest of the houses and the buildings, this doesn't come into picture later, right? Similarly, you plan power grid in a SOC. You plan your VDD and ground signals. Entire power grid is designed before you go about placing your gates and other components. If you go next. So if you look at an SOC scenario, you would have designed which are all my different voltage regions, power islands, and there are many complications when you come up with a power plant, especially when you're talking about a low power design for a mobile kind of an application. You have to take all the parameters into consideration when you are designing a grid. Similarly, when you look at a city, you'll also have to look at where are all the maximum usage of water and sewage will be there. You will have to provide bigger channels there, things like that. So it's similar to power. You can think like power supply as a water supply and ground as a sewage channels. So similarly, you have to plan for a SOC how you supply the power and ground. Go next. So once you have planned everything, then you lay out in the layout so that all components get proper power supply. And you also have to do IR drop analysis to ensure this power grid is intact. We go to the next one. Next, Hari.
Yeah, this all in text placement and CTS.
Yeah, next one. Yeah. So the next aspect is how do we place the houses. So similar analogy, if you want to take in a SOC, you would be placing all the gates. So the next step is once you have power ground and floor planning is all done, then you start placing your houses and buildings in a city. And similarly, you would go ahead and place all your gates and logic components in an SOC. Next one. So again, when you are placing, you need to ensure that you have proper. Once houses are built, you need to have electric supply properly given. I call that as equivalent to a clock supply. Right? Clock is an important component which stimulates the entire logic. Right? So it's a synchronous design. So clock has to reach all the sequential elements so that logic can operate. So it's equivalent to, you can think of it as electrical supply. So you have a power grid from where you have to supply all the electrical supply to all your houses and buildings and so on. Similarly, you have a clock tree which is built to supply the clock to all the cells, all sequential cells in the design. So you can take that as an analogy. So that's what we achieve in clock synthesis. If you go next. So then the next step is routing. So you can think of routing as building your roads, the connectivity to each house. So the similar way you connect all the houses using your road network, you will have to do signal routing to connect all the gates in the design based on the gate level connectivity defined in a gate level netlist. You hit next. So the biggest problem that you see in routing is similar to what you have in city road conditions, which is the congestion of traffic. You will have congestion of routability in the design. So that will be the key challenge that you have to address. If you go next. So normally what we use when we have a lot of congestion, city traffic congestion, we use flyovers. So similar to that, we have multiple layers of metal layers that we use for routing the signals. So if you look at the latest technology nodes, we probably have like up to 14, 15 metal layers. So so you have so many metal layers to route the signals, and you also understand the complexity, right? You have millions and billions of gates that need to be connected. So you would need so many layers to connect them. So with that, I thought I gave you an overview of what physical design is. I also want to give a glimpse of what a physical design engineer role in VLS industry is, or how do you prepare yourself to be a physical design engineer. So keep hitting next. So first and foremost is I would strongly encourage to have strong CMOS and FinFET device physics and circuit design fundamentals. That's a key aspect for physical design. And then you also need to learn, when you are at college, you have to learn the aspects like latch-up, design rules, short channel effects, again, part of your device physics, and manufacturing process, lithography steps, and so on. So that is very important for a physical designer to understand the technology as well as device physics. Next thing that I would strongly encourage everyone to have is basic Unix operating systems, programming and scripting languages. While I say semiconductor jobs may not require as much programming scripting, but it is very much computers and EDA tools is what we will be working with. So programming and scripting languages is very much needed. And it's also important to have awareness or experience of industry standard EDA tools. So when I talked about all this physical design, right, how are we achieving this? It's mainly through EDA tools, what we call it, electronic design automation tools. Cadence, Synopsys, Mentor are the companies which have these EDA tools. So if you have awareness of these EDA tools, or if you have used these tools, that will help tremendously for physical design role in your industry. And if you go through Google or internet, you have so many blogs and tutorials available on physical design, manufacturing process, technology, like what is 7 nanometer technology, what it is. So if you go through those search results, you will understand fair bit of information in terms of what it takes to do physical design for a chip. And I would strongly encourage, if you feel, yes, this is exciting to me, and I feel, okay, this is very interesting and state of the art, I want to work on this field. I strongly encourage you to look at a relevant project work in physical design, or maybe go through some trainings to get an understanding of. I mean, I have compressed everything in 40 minutes, but it's much more than that, much more than what I have talked about. So if you do a project, that will definitely help. And last but not the least, I would always encourage you to focus, give emphasis on presentation and communication skills, and then also teamwork for engineers. So those are the two aspects you will have to focus, and if you have some means of developing these skills, you should definitely focus on those. And lastly, you should have eagerness and enthusiasm to work on cutting edge technologies. And when I talk about physical design, we are talking about cutting edge, latest technologies and nanometers era. So it's ever changing, constantly learning process. And in fact, if you ask me, I've learned and studied more after I came out of college and started doing physical design than I have studied at college. So it's an ever learning process, and if you have enthusiasm, eagerness to work on these cutting edge technologies, definitely you can choose a physical design career. So with that, I conclude. I'm open to take questions.
Am I audible?
Yes, Hari.
Okay, let me read out the questions. Yeah. So, what is the internal and external power switch, and what all the pins in power switch and connections power switch? The first part of the question.
Okay. So yeah, let me talk about internal and external power switch, right? So you can have a power supply switch to a part of your logic or to entire chip, either through an external chip which is again which will have a power switch in it, or you can have internal switches which will be operated through a power gating logic. So you can, for example, let me talk about an application. Right? Let's say I'm using a mobile phone. I'm using display. At that time, I'm not using modem. Let's say I'm not taking a call while I'm using display. I can always switch off the modem part of the design and enable the display and multimedia part. So that internal switches can do that. So it's a logic function that will switch different parts of the logic at different operating time
Yeah,
frames.
there are two other parts. Yeah, let's go through quickly. Many questions. So,
Yeah,
what all the
right.
questions can be raises from the power switch?
What all
Questions
the questions can be?
that can be raised from the power switch. I don't know. It's not very clear. Let's skip it. What are the scenarios
Yeah.
generally we are enabled at a placement and CTS stage?
What are the scenarios
We enable
generally
at the placement and
enabled?
CTS stage. We get the power switch.
With respect to power switch, yes. I mean, if you are going for a design with the power switches, you need to have either a and you have to decide first what is your power switching strategy, right? It can be a distributed power switching or power ring kind of a structure. If you are making a specific ring around a network and you want to switch off that, that is one method of switching. Or you have distributed switches which are like a logic gates spread across the design, placed across the design, and those can be switched with a sleep signal that again your functionality will decide when they have to be switched off, and you can use that distributed power switching. So if you are using distributed power switching, yes, during placement you have to take care of that.
Next question. What are the main challenges in PD of MBC FET or a gate around transistors? What are the possible solutions for it?
MBC FET. I'm not sure what this means. If it is if they're referring to multi-bias designs, yeah, I think it may be the multi-bias. Okay, so if you have multi-bias, and most of it is designed within the standard cells itself, you will have a signal to enable or disable the bias. It's mainly for power, low power design. So if you want to bias your transistors so that your threshold voltages can be altered and hence your performance can be changed depending on the scenario. Let's say if you want to use it in a turbo mode, you want to have higher performance, then you can. But then when you play with your bias, the leakage will vary. So you will have higher leakage when your performance goes
Okay.
up.
The next question, like how machine learning is growing or going to be used in VLSI industry, especially in the physical design.
Oh, it's an interesting question. Yes, I mean we are using several placement routing algorithms, and I told you about iterative process, right? You do multiple iterations on each step. So can all these iterations be automated using a machine learning algorithm? That's where a lot of it is being explored. I mean, yes, there's a lot of work happening in the industry on machine learning for physical design, right? You so that your engineer's work and effort is minimized. So most of the iterations that you perform can be done with a ML algorithm.
Yeah, please.
That's one application. I think there are multiple places where ML is getting applied.
Okay, please explain physically unclonable function.
Physically unclonable function. So, for example, uh, if you have a design which has to operate at different operating conditions, then and most of the design is physically unclonable. In fact, if you look at any cloning that you do, any gate, if you look at exact physical parameters, for example, input transitions, output transitions, the way power supply is given to that particular gate, all of that will be physically different. It's same AND gate. If you are placing it in different places in the design, will have different operating conditions. So, in that sense, lot of all the even though it is a logical clone, physically they will be exclusive entities.
Yeah. What are the major differences between technologies like nanometer, 14 nanometer to 5 nanometer?
Oh yeah, it's once you start packing a lot of things into smaller regions, different aspects of signal integrity, different aspects of power integrity. Uh, I mean, the closer you bring, uh, things become tougher in terms of parasitic effects, parasitic capacitances, and its effects on the transistors. And the other problem is the transistor is so small that very small current can turn on the gate, right? So your transistors are very sensitive for any fluctuations, both in terms of power supplies or inputs outputs. And then you have so much of parasitics in the metal rods that are coming into picture, which will become which will aggravate the problem of transistor functionality. So yeah, I mean, I can talk for hours on this topic. What are the different challenges that we'll encounter when you go to lower technology nodes? But in essence, yes, the shorter distances will cause a lot of signal and power integrity issues and so on.
Do we have a good career in physical design nowadays? The tool is getting automated, and what is the option? Would you say, please?
Yeah, even automated tools have to be run by an intelligent person. So obviously, you have a lot of opportunities in physical. In fact, if you look at the number of engineers required for a chip design, physical design engineers occupy quite significant amount of people. So in that sense, yes, physical design will have a lot of career opportunities.
Are there any open source tool for physical design that can be used till GDS2?
Yeah, I mean, there are some open source tools. I'm not sure if they are any more relevant now, because even if you use them, they are very rudimentary and preliminary. I mean, they may not give you the exact challenges that you face in a real-time designs that you would work in an industry, right? Yeah, I think there are some tools, but they are not very effective or relevant nowadays.
Yeah, next question. What part of the PD can delay the tape out time most often?
Any part, right? If you have not done floor plan right, if you have not done placement right, anything that in the entire physical design flow, if things are not checked or done properly at each stage, it can eventually hit. See, at the end of it, you have to run all the checks, sign off checks. That's where you will find all the issues. And for those final sign off checks to pass the first time, all the things have to be done right from the beginning. So once everything come together, that's when final sign-off checks will go past easily.
Okay. So what kind of difficulties do we come across in PD when working with RFIC or RFSOC?
Yeah, it's RF is in terms of physical design complexity, RF chips may not be highly complex, but RF components internally will have a lot of physical design challenges. It's more like an analog layout kind of. What I talked about is digital design, physical design. What we talked in today's talk. But if you're talking about physical design, often analog component, that's entirely different ballgame altogether. But if you go to RF, yeah, it's 10 times more complex than regular analog components that you design.
Yeah, there are many other questions, but there are people from the industry, so I'm not sure. Yeah, don't have time to take all those questions. Let me ask this: how full chip partitioning will divide the complete die like sub blocks?
Oh yeah, so I think I explained through that analogy, right? City planning. So you first have to look at how you want to partition your entire chip based on connectivity, based on functionality, and the operating conditions in which all these multiple logic functions operate. Based on that, you have to first start partitioning and come up with placement of those partitions in a chip level.
Okay. And the last couple of questions, right? So does the packaging type PGA, CSP, or any other affect the electrical parameters? Which packaging type is most reliable?
I mean, it again depends on the application that you're talking. If you're talking about a satellite application versus a military application versus a mobile chip versus a data center chip, it's very much packaging is all dependent on the application. And the first question is, does it impact electrical parameters? Yes, definitely it does. For example, if you go to a flip chip BGA chip, which will give you a better power integrity performance on die versus a wire bond chip or some other package, right? So yes, they will impact electrical parameters, and the type of package that we choose depends on very much on the application.
Yeah, probably the last question. Someone my student is asking, how do I get into SemiConnect as a BTech graduate? I think you should do it more like how people should get employed. Actually, that's really rephrase the question.
Okay, so SemiConnect is mainly a expert freelancer platform, so it's not for students. Sorry to say that, but to explain how people can get into industry, like I said, have your strong fundamentals and get exposure to the EDA tools, either to a training institute or if you have your university is providing the tools. Please get exposure to the tools. That's where you will have an edge over others. And last but not the least, go through a lot of material available on the web. So you have a lot of tutorials, lot of blogs available, which you can go through and start learning.
Yeah, I think we've come to the end of the presentation. Madhu, you want to do a vote of thanks? Madhu, are you there? Madhu? Yeah, Madhu.
Okay, I was just trying to show the next webinar that we have, which is on the 9th of October. This is in the FPGA system designed by Mr. Shrikant Neelam. First, I would definitely like to thank Sudheer for such a wonderful presentation. It's so easy to understand for the students. I think it was really giving examples of real life and how that can connect. And I think that should have been a very easily understandable topic for most of the students. So thank you so much, Sudheer. Thank you for taking time and doing this for us.
Thanks, Madhu.
Yeah. All right. So we also have the feedback form. We have put the link on the chat session. So please fill up the feedback form, and you get the certificates from IEEE, VLP, and Springbok. And we look forward to seeing you again in the next session, which is on 9th of October.
Thank you, everyone. Bye-bye.
Right. Thank you, everyone.
Bye-bye from all of us in the Springbok. See you then.
Yeah.
Okay. Thank you, everyone. Bye.
Yeah. Bye.